Let us now study the t-statistic more closely and just start from its definition. Estimator minus quantity under the null divided by the standard error. Notice that we can plug in the expression for rho hat -1 we derived in the previous video. And after some rewriting, we arrive at this expression over here. In this expression, you should recognize our numerator and the denominator. But let's zoom in on the new ingredient, which is the sample variance of the residuals, as defined over here. How do we continue with our derivations? Well, we can plug in the DGP indicated in blue. YT is nothing more than YT -1 plus UT. And then I take the terms with the lagged Y together, and I keep the error term UT separately. And then I expand these terms, and I arrive at these three terms over here. Just like I did in week 3, I can then write down the stochastic orders of the terms below. I know that if I blow up this guy over here by t, it converges in distribution because I looked at its limiting distribution in the previous video. So this term is of order OPT to the power -1. And the squared term here is then nothing more than the square of 1 over t. The other terms are the numerator and the denominator from my previous derivations. And I know that the scaling of the numerator was 1 over t, and the scaling of the denominator was 1 over t squared. So I also know the stochastic orders of these terms. And if you put all of the pieces together, you see that the only remaining and dominant term is the one with the squared errors to use. So this last guy over here. All the others will vanish in the limit. And I know that this term, this last guy, converges in probability to the expected value of the squared errors, which was defined as gamma naught in the previous video. Now, of course, this should also not come as a surprise that here the sample variance converges in distribution to gamma naught. Collecting all the ingredients on the next slide, we then see that the limiting distribution of the t-statistic also contains the nuisance parameters gamma naught and lambda squared. So also here, I can't directly simulate from this limiting distribution. What can we then do instead to arrive at a test statistic that is free from nuisance parameters? Well, let us start with this test statistic over here. And let us start from the limiting distribution of this test statistic that we have obtained. The key idea is that I will try to rewrite this limiting distribution as a part that is free from nuisance parameters and a part that still contains nuisance parameters. Why do we do that? Well, that will become clear in a minute. So let's start from our limiting distribution and do some rewriting by adding and subtracting the long run variance lambda squared. Then I can take these terms together in the first part, where I've pulled lambda squared outside. And I'm only left with this second part over here in my second term. Now the red part over here is highlighted since this should be familiar to you. It's the regular Dickey-Fuller distribution that you would obtain when there is no serial correlation in the error terms because the lambda squareds cancel out. So the lambda squareds cancel out and you have the regular Dickey-Fuller distribution. So in case I would have a test statistic with this limiting distribution, I would be able to simulate from that again, just like last week. Unfortunately, our test statistic does not converge to the limiting distribution, this red guy over here, but there is a second term. And that is the second term where I have separated out the nuisance parameters. That's where the nuisance parameters pop up. But I managed to separate them out in this term. And why is this useful? Well, this suggests that I can correct my original test statistic by subtracting a sample counterpart of this second term. And why is that useful? Well, if I subtract a sample counterpart from this second limiting distribution over here, then this new test statistic would just simply converge to the red limiting distribution, the Dickey-Fuller distribution, which is free of nuisance parameters. And in this line over here, I indeed plug in all of the sample counterparts of this second term over here. We need a consistent estimator of our long-run variance. We also know that the sample variance converges in probability to gamma naught. And we also recognize here the denominator from which we know that it converges to this limiting distribution. So in essence, we rewrote the limiting distribution of our regular test statistic in two parts, the Dickey-Fuller distribution, free of nuisance parameters, and a part that contains the nuisance parameters. If we then subtract from our original test statistic the sample analog of that second term that contains all the nuisance parameters, we do converge to the Dickey-Fuller distribution in red, free of nuisance parameters from which we can simulate again to obtain the critical values, like we did last week. So we looked at the trick for this test statistic, so sample size times rho hat minus 1. But we also have another test statistic, our regular t statistic. Can you do the same trick over here? Well, yes. Break it up again in a part where you recognize the limiting distribution from last week that didn't contain any nuisance parameters, and a part that depends on nuisance parameters. I summarize here all the key ingredients on this slide, such that you can look back at this. On the next slide, let's start from the definition of the t-statistic. And first, we will try to get rid of the gamma naught and the lambda squared in the denominator over here. I can do that by multiplying by gamma naught. And when I add an extra lambda factor, as I will try to cancel that one out again with the ones in the top, like I did for the previous test statistic. Now, if I multiply by these factors in blue over here in the limiting distribution, then of course I need to multiply the test statistic by their sample counterparts, which I do over here. On the next line, I then do the same trick from before, subtracting and adding the long-run variance such that I can regroup my limiting distribution in one part that is free of nuisance parameters and another part that contains the nuisance parameters. And that last line suggests then already that I can retransform my test statistic by pre-multiplying by this factor and by subtracting the sample counterpart of this second term over here, such that I have a new t-statistic, this guy over here, that converges to the red limiting distribution from last week, which is free of nuisance parameters. Now, before wrapping up this video, some concluding remarks still on the Phillips-Perron test statistic. Note that we relied on linear processes and the Beveridge-Nelson decomposition to establish our derivations. But also for other dependent processes, we have this uniform convergence result, but we will not look into those results in this course. In practice, the test statistic that we will discuss next, namely the augmented Dickey-Fuller test, is also actually preferred over the Phillips-Perron test, as this long-run variance estimator only slowly converges. Also in the boot UR package, we only implemented the AGF test for that reason.